Before there were stars, before atoms, before time had direction, there were numbers, not written, not spoken, not imagined, but embedded. When physicists look deeply into nature, they discover something unexpected. The universe does not merely behave, it behaves according to precise numerical values. These values appear again and again in equations, in experiments, in distant galaxies, in the earliest light of the cosmos. They are called physical constants. They do not change, they do not negotiate, they do not drift. The universe seems to insist on them. And this raises a quiet but profound question. Why does the universe have these constants and not others? This is not a religious question, not a mystical one. It is a scientific question asked seriously by some of the greatest physicists who ever lived. What physicists mean by physical constants? In physics, a constant is not simply a convenient number. It is a value that appears in the fundamental laws of nature, is the same everywhere we look, does not depend on time or location. If you measure an electron on Earth, near a distant quasar, billions of years in the past, it behaves exactly the same. That universality is astonishing. Physical constants determine how strong forces are, how fast information travels, how matter holds together, whether atoms, stars, and life are possible. They are not properties of objects, they are properties of reality itself. The speed of light, the first constant. Let us begin with one of the most famous constants, the speed of light, c. Value, 299,792,458 meters per second. This number is not just about light, it is the maximum speed of causality, the conversion factor between space and time, the backbone of Einstein's relativity. Nothing carrying information can move faster. If this number were even slightly different, time would behave differently, mass-energy equivalence would change, the structure of space-time itself would alter. Einstein showed that c is not a property of light, it is a property of space-time. Reference: Einstein on the Electrodynamics of Moving Bodies, 1905. Already we see something strange. Reality has a speed limit and it is written as a number. Gravity's number, the gravitational constant. Now we turn to gravity. The gravitational constant, g, value 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. This tiny number determines how strongly masses attract, whether stars ignite, whether galaxies form. If g were slightly stronger, stars would burn too fast, the universe would collapse quickly. If g were slightly weaker, matter would never clump, stars would never form. Gravity is extraordinarily weak compared to other forces, yet precisely strong enough to shape the cosmos. This delicate balance disturbed many physicists. Paul Dirac famously noted that gravity's weakness appears numerically unnatural. Reference: Dirac, The Large Numbers Hypothesis, 1937. Again, the question returns: why this number? When physics entered the 20th century, something unexpected happened. Reality stopped being smooth. Planck's constant, h, value 6.626 times 10 to the negative 34 joule seconds. This number governs quantum discreteness, energy levels of atoms, uncertainty, and the very existence of quantum mechanics. Max Planck introduced this constant in 1900, not because he wanted to, but because classical physics failed completely to explain black body radiation. Energy, it turned out, is not continuous. It comes in packets, quanta. Planck's constant sets the smallest meaningful action in nature, the scale at which classical intuition breaks. If h were larger, atoms would be unstable, chemistry would dissolve. If H were smaller, quantum effects would vanish, stars could not ignite properly. Planck himself called this discovery an act of desperation. Reference: Planck on the law of distribution of energy in the normal spectrum, 1900. A single number quietly separates certainty from probability, determinism from uncertainty. The fine structure constant, the most mysterious number. Now we encounter a number that has unsettled physicists for over a century. The fine structure constant, alpha. Value to 1 over 137.03599. This dimensionless number controls strength of electromagnetism, atomic structure, chemical bonding. It appears everywhere: atomic spectra, quantum electrodynamics, stellar processes. Richard Feynman once said, "It has been a mystery ever since it was discovered. All good theoretical physicists put this number up on their wall and worry about it." Small changes in alpha would cause atoms to collapse, electrons to escape nuclei, chemistry to cease. Unlike other constants, alpha has no units. It is a pure number. That makes the question sharper. Why this number and not 1 over 136 or 1 over 140? This is one of the deepest unsolved questions in physics. The universe contains particles, electrons, quarks, neutrinos. Each has a mass. But here is the unsettling part. The standard model does not predict these masses. They are inserted by measurement. The electron mass determines atomic size, controls chemistry, governs biology. If it were just 2 to 3 times heavier, stable molecules would be rare. Quark masses determine whether protons are stable, whether neutrons decay, whether nuclear fusion works. Why do these masses fall into a narrow, life-permitting range? Even Steven Weinberg admitted the standard model contains many arbitrary parameters. Reference: Weinberg dreams of a final theory, particle data group. These numbers appear selected yet unexplained. The cosmological constant, vacuum with a number. Perhaps the strangest constant of all. The cosmological constant, L. It describes the energy of empty space, the acceleration of cosmic expansion. Observed value, incredibly small, but not zero. Quantum field theory predicts a value 120 orders of magnitude larger than observed. This is known as the worst theoretical prediction in physics. If L were slightly larger, galaxies would never form. If slightly smaller, the universe would collapse early. Steven Weinberg showed that observers can only exist in universes where L is tiny. This result later influenced the anthropic principle. Reference: Weinberg, 1987, Anthropic Bound on the Cosmological Constant. Rees et al., 1998, Accelerating Universe. Once again, a number, finely constrained, unexplained. Modern physics has learned something profound. The universe is built on symmetry. Symmetry in physics does not mean beauty. It means invariance, something that does not change when conditions change. Examples: rotate space, laws remain the same. Shift time, laws remain the same. Change reference frame, laws remain the same. From these symmetries arise conservation of energy, conservation of momentum, conservation of charge. This connection was formalized by Emmy Noether in 1918. Every continuous symmetry corresponds to a conserved quantity. Reference: Noether, Invariant Variations Problema, 1918. But here's the key insight. Constants appear when symmetries are broken. In the early universe, temperatures were immense, forces were unified, distinctions did not exist. As the universe cooled, symmetries broke. This is called spontaneous symmetry breaking. It is not imposed from outside. It happens naturally when systems settle into stable states. The Higgs field is a prime example. The Higgs mechanism. Particles gain mass because the Higgs field has a non-zero value everywhere. That value determines electron masses, quark masses, weak force strength. The constants we measure today may be frozen remnants of early universe phase transitions. Once the universe cooled, those values became fixed, like cracks forming as water freezes. This suggests constants may not be arbitrary, but historical. Quantum field theory reveals something unsettling. Constants are not always constant. They run. The strength of forces depends on energy scale, distance. This is described by renormalization group equations. For example, electromagnetic coupling increases at higher energies. Strong force weakens at shorter distances. Yet at everyday scales, the values appear fixed. This leads to a subtle idea. Constants are effective descriptions, not ultimate truths. At deeper levels, different physics may operate, with fewer parameters. The constants we observe may be surface features, emergent numbers. Physicists often expect dimensionless constants approximately 1. But many constants are extremely small or extremely large. This is called the naturalness problem. Examples: gravity is 10 to the 38th times weaker than electromagnetism. The cosmological constant is absurdly small. Paul Dirac argued that such large ratios demand explanation. This motivated grand unification theories, supersymmetry, extra dimensions. So far, no experimental confirmation. This leaves physicists uneasy. Either deeper laws explain these numbers, or our expectations are wrong. Reference: Dirac, 1937, Tufte, 1979, Naturalness criterion. The universe may not care about our sense of elegance. One of the most subtle ideas in modern physics. Perhaps some constants are what they are because we exist to observe them. This is the anthropic principle. Imagine a universe where alpha is slightly different, gravity is weaker or stronger, the electron mass shifts. In such universes, complex chemistry cannot exist, stars may never form, life as we know it could never emerge. Steven Weinberg noted, "We observe the cosmological constant to be small because otherwise galaxies would not exist and we would not be here. We find ourselves in a universe compatible with life simply because we exist here." Strong anthropic principle. The universe must allow observers to exist. For physicists, this principle is controversial but mathematically consistent. It gives a framework for why constants fall into a life-permitting range without invoking deeper laws yet undiscovered. The multiverse and the string landscape. To go deeper, we must venture into string theory. String theory suggests fundamental particles are vibrating strings. Extra dimensions exist, 6 or 7 hidden dimensions. The vacuum is not unique. This leads to the string landscape, roughly 10 to the 500th possible ways the universe could settle, each with different constants. In some universes, gravity is stronger, electron mass is higher, cosmological constant is enormous. We exist in one of the very few universes where life is possible. If this is true, constants may not need deep explanation. They are environmental, selected by our existence. But this does not answer why physics is mathematical or why the landscape exists at all. Even with multiverse reasoning, renormalization, and symmetry breaking, some questions remain fundamental. Why do numbers exist at all? Why does mathematics describe reality so well? Why is there a universe rather than nothing? Physicists such as Max Tegmark have suggested the mathematical universe hypothesis. The universe is mathematics, and constants emerge naturally from the structure of mathematical reality. Reference: Tegmark, Our Mathematical Universe, 2014. Other scientists caution that some constants may be brute facts, true, fixed, and ultimately unexplainable by deeper theory. This is not defeat, it is recognition that some mysteries are intrinsic to the cosmos. Towards a deeper understanding. So far, we have traced c, speed of causality, g, gravity's whisper, h, quantization of action, alpha, the strength of electromagnetism, particle masses, tuning the chemistry of life, and lambda, the energy of empty space. Then we explored symmetry, symmetry breaking, renormalization, naturalness, anthropic selection, and the string landscape. All of these suggest one profound truth. Constants are not arbitrary in effect, even if some may be arbitrary in origin. They govern the possibility of complexity, life, and consciousness itself. The universe speaks in numbers. We listen, we measure, we wonder. And still, the question remains, why these numbers and not others? It is a question that bridges physics, philosophy, and quiet contemplation. Beyond alpha, the electromagnetic force has two fundamental constants: permittivity of free space, epsilon, 0, value approximately 8.854 times 10 to the negative 12th farad per meter, governs how electric fields propagate in vacuum. Permeability of free space, mu0, value 4 pi times 10 to the negative 7th newtons per ampere squared, governs how magnetic fields propagate in vacuum. These constants determine the speed of light, c equals 1 over epsilon 0 times mu 0. Reference, Jackson, Classical Electrodynamics, 3rd edition, 1998. Implication, c is not independent. It emerges from electromagnetic vacuum properties. Small changes in epsilon 0 or mu 0 lead to altered light propagation. Atomic instability, chemistry fails. This is an example of constants interdependence, a subtle but profound fact. Boltzmann constant, linking temperature and energy. The Boltzmann constant, K, bridges thermodynamics and microscopic physics. Value 1.380649 times 10 to the negative 23rd joules per K. Converts temperature K into energy scale. Example, thermal energy per particle approximately kT. Determines when atoms vibrate enough to break chemical bonds. Without this number, stars could not sustain fusion. Life-supporting chemistry would fail. Reference, Boltzmann, Lectures on Gas Theory, 1996 to 1998. Interestingly, K is not dimensionless. Its value depends on human units, but it sets the scale at which statistical physics and thermodynamics operate. Some constants relate to counting particles. Avogadro number, n sub a, value 6.022 times 10 to the 23rd particles per mole, connects microscopic and macroscopic worlds. Universal gas constant, R equals K times n sub a, appears in PV equals nRT. These constants define scales of chemistry and biology, allowing precise predictions of reactions and molecular interactions. Reference, NIST, Fundamental Physical Constants, 2022. They demonstrate how constants bridge scales from quantum to human-experienced reality. Paul Dirac noticed astonishing numerical coincidences. Ratio of electric to gravitational force between proton and electron, about 10 to the 39. Age of the universe in atomic units, about 10 to the 40. These large numbers are similar in magnitude, raising a question, coincidence, or fundamental law. Dirac proposed the large number hypothesis, 1937. Certain constants may vary slowly over cosmic time to preserve these ratios. Modern observations constrain such variation very tightly, but the coincidence remains mysterious. Reference, Dirac, The Cosmological Constants, 1937. Usen, Varying Constants, Gravitation and Cosmology, Living Review Relativity, 14, 2, 2011. This hints that constants may encode deep cosmological structure, not just particle-scale physics. Max Planck noticed something remarkable in 1899. We can combine fundamental constants to define natural units that do not depend on human conventions. Key Planck units. Planck length, or L sub p, L sub p equals the square root of h bar g over c cubed, approximately 1.616 times 10 to the negative 35 meters. Smallest meaningful length scale in physics. Below this, classical spacetime ceases to make sense. Planck time, or T sub p equals the square root of h bar g over c to the fifth, approximately 5.39 times 10 to the negative 44 seconds. Shortest meaningful time interval. Planck mass, or m sub p equals the square root of h bar c over g, approximately 2.18 times 10 to the negative 8th kilograms. Scale at which quantum effects of gravity become strong. Reference: Planck, über irreversible Strahlung, 1899. Z, Quantum Field Theory in a Nutshell, 2010. Planck units unify c, g, and h, hinting at a fundamental interconnection between relativity, quantum mechanics, and gravity. Physicists love dimensionless constants, numbers that have no units, independent of human measurement systems, encode pure relationships in nature. Examples: fine structure constant, alpha, approximately 1 over 137. Proton to electron mass ratio, MP over ME, approximately 1836. Cosmological constant in Planck units, lambda times L sub p squared, approximately 10 to the negative 120. Dimensionless constants are especially mysterious. Why 1 over 137 and not 1 over 140? Why 10 to the negative 120? Reference: Okun, The Fundamental Constants of Nature, 1991. These numbers encode deep structure without reference to meters, kilograms, or seconds. Advanced research shows that some constants are tightly linked. C, epsilon sub 0, mu sub 0, electromagnetic speed of light, C equals 1 over epsilon sub 0, mu sub 0. Planck units combine h, c, and g to define natural length, time, and mass. Alpha combines e, epsilon sub 0, h, and c. Alpha equals e squared over 4 pi epsilon sub 0 h bar c, approximately 1 over 137. These relationships hint that the constants are not isolated. They emerge from a deeper interconnected mathematical framework. Reference: Duff, Comment on the Nature of Fundamental Constants, 2002. In other words, changing one constant arbitrarily may be meaningless. The laws themselves conspire to keep ratios and relationships stable. In modern physics, constants appear in thermodynamics and information theory. Boltzmann constant, K, links temperature and energy. Planck constant, H, connects energy and frequency. C limits the propagation of information. G bounds the information content of spacetime. Stephen Hawking and Jacob Bekenstein discovered that black hole entropy is proportional to area. This equation shows all 4 fundamental constants together, encoding gravity, quantum mechanics, relativity, and statistical mechanics. Reference: Bekenstein, Black Holes and Entropy, 1973. Hawking, Particle Creation by Black Holes, 1975. Remarkably, constants define the limits of information in the universe. They're not abstract, they govern reality itself. We have now completed sections 21 to 24, covering Planck units, natural scales, dimensionless constants, interrelations among constants, constants in entropy, information, and black holes. We briefly mentioned lambda before, but let us go deeper. The cosmological constant, lambda, represents energy density of empty space, acceleration of cosmic expansion. Quantum field theory predicts a vacuum energy density, p-vac, similar to E Planck to the 4th over h bar cubed c to the 5th, approximately 10 to the 120 times observed value. This is the famous cosmological constant problem, the largest known discrepancy between theory and observation. Lambda shows that constants are not just numbers, they encode the very structure and fate of the universe. Higgs field and vacuum expectation value.
The Higgs field gives mass to fundamental particles. Vacuum expectation value, approximately 246 GeV, determines the masses of W and Z bosons, quarks, and leptons. Tiny variations in the Higgs vacuum expectation value, if slightly larger, protons decay rapidly. If slightly smaller, stars may not ignite. Reference: Higgs, 1964, Broken Symmetries and the Masses of Gauge Bosons. Atlas and CMS, 2012, Higgs boson discovery. The Higgs constant is not dimensionless, but it directly sets the scale of all particle masses, linking microphysics to cosmic stability. Neutrino masses, small but significant. Neutrinos are tiny, almost massless particles. Masses are 0.01 to 0.1 eV, approximate experimental constraints. Detected through oscillation experiments, Super Kamiokande, 1998. Though small, neutrino masses influence cosmology, structure formation in the universe, cosmic microwave background anisotropies, matter-antimatter asymmetry through leptogenesis. Reference: Fukuda et al., Evidence of Oscillation of Atmospheric Neutrinos, 1998. Planck collaboration, Cosmological Parameters, 2020. These small numbers are constants of a subtle kind, tiny values with massive consequences.
Many constants are interconnected in vacuum stability. Higgs mass, top quark mass, strong coupling constant. If slightly different, the electroweak vacuum could be metastable, leading to decay over cosmic time. This demonstrates a subtle, fine-tuning problem. Constants are not random. Small shifts lead to entirely different universes. Some physicists view this as evidence for anthropic selection, underlying multiverse landscape. One of the most powerful ideas in theoretical physics is grand unification. At extremely high energies, electromagnetic force, weak nuclear force, strong nuclear force may become one single interaction. This is supported by renormalization group equations, which show that the coupling constants of these forces change with energy. When extrapolated to very high energies, alpha, electromagnetic, alpha S, strong, alpha W, weak, begin to approach similar values. This suggests something profound. The constants we measure today may be low-energy remnants of a simpler, unified constant. In other words, constants are not independent. They may be shadows of a deeper symmetry. Proton stability and constants. The stability of matter depends on delicate numerical balances. The proton appears stable, but many theories predict it could decay. Proton lifetime depends on unification scale, coupling constants, matter masses. If constants were slightly different, protons might decay in seconds. Chemistry would be impossible. Experiments like Super Kamiokande place lower bounds on proton lifetime, 10 to the 34 years. Reference: Super Kamiokande collaboration, 2014, PDG, proton decay limits. This shows that constants silently protect matter, structure, time itself. Constants and the arrow of time. Constants do not just shape space, they shape time. The second law of thermodynamics depends on Boltzmann constant, K, and initial conditions of the universe. The low entropy of the early universe is one of the deepest puzzles in physics. Roger Penrose estimated the probability of such low entropy initial conditions as 1 part in 10 to the 10 to the 123. Without this extreme numerical tuning, time would have no direction. Memory, evolution, and causality would fail. Thus, constants influence not just what exists, but how existence unfolds. Advanced observations test whether constants vary over cosmic time. Measurements include quasar absorption spectra, atomic clocks, cosmic microwave background. Results so far: variations are extremely constrained. If they vary at all, changes are tiny. If any variation were confirmed, it would revolutionize physics, imply new fields or dimensions. For now, constants remain astonishingly stable, universally consistent. At the deepest known level of physics, something unusual happens. The familiar constants, c, g, h bar, no longer behave as separate quantities.
In attempts to quantize gravity, space-time itself becomes uncertain. In loop quantum gravity, area and volume are quantized. Planck length emerges as a minimum scale. Geometry becomes discrete. In string theory, particles are excitations of strings. Constants depend on how extra dimensions are compactified. In both approaches, constants may not be fundamental at all. They may be emergent properties of deeper structures. Reference: Rovelli, Quantum Gravity, 2004. Polchinski, String Theory, Volume 1 and 2, 1998. This suggests a radical idea. Constants may arise the way temperature arises, real, measurable, but not fundamental. The holographic principle: constants and information. Black hole physics revealed something extraordinary. Jacob Bekenstein and Stephen Hawking showed that the maximum information in a region of space depends on surface area, not volume. This led to the holographic principle. According to this idea, all physical information in a volume can be encoded on its boundary. Here, constants reappear in a new role. G limits information density. H-bar sets quantum discreteness. C constrains signal propagation. Reference: Toft, 1993. Susskind, The World is a Hologram, 1995. In holographic theories like ADS-CFT, constants in one theory map to parameters in another. Gravity and quantum field theory become dual descriptions. Constants, therefore, may be translation keys between equivalent realities. Mathematical inevitability. Are constants forced to exist? Some physicists believe constants are not chosen at all. They are mathematically inevitable. In this view, consistent mathematical structures exist, only some are self-consistent. Fewer still allow complexity. The universe may simply be one of the very few consistent solutions. This echoes ideas proposed by Einstein, search for inevitability; Wigner, unreasonable effectiveness of mathematics; Tegmark, mathematical universe hypothesis. Reference: Wigner, The Unreasonable Effectiveness of Mathematics, 1960. Tegmark, Mathematical Universe Hypothesis, 2014. If this is true, the constants are not accidents, they are consequences. We began with a simple question: why does the universe have these physical constants? Along the way, we discovered constants govern forces, particles, space, time, and information. Some emerge from symmetry and symmetry breaking. Some depend on cosmic history. Some may be environmental. Some may be mathematically unavoidable. Some may remain forever unexplained. What physics tells us, honestly, is this: the constants are not random in their effects. Whether they are random in origin remains unknown. The universe speaks in numbers. We listen, we measure, we build theories, and we accept uncertainty where certainty ends. For now, the constants remain steady, silent, precise, holding together atoms, stars, galaxies, thought itself.
If you enjoy exploring the universe slowly through physics, ideas, and unanswered questions, you may enjoy the other quiet explorations on the Wandering Neuron. Thank you for listening.